Hello there, welcome to Ethio-Hahu tutorial. Last time we have seen about uniform circular motion and uniformly accelerated circular motion. In addition to that, we have seen uniform circular motion in a horizontal circle and circular motion in a vertical circle. Today we are going to see about dynamics of circular motion. How can a car round a curved path? Let's consider a car turning at the corner of a level curved road. For a car moving around a flat curved road, the centripetal force comes from the frictional force between the tires of the car and the road. And this frictional force acts as a centripetal force. Therefore, for a car turning around a level curved road, for a car turning around a flat curved road, the centripetal force comes from the frictional force between the tires and road. That is, centripetal force is equal to simply frictional force. This is equal to coefficient of friction times normal force. And since the car is on a flat curved road, the normal force is equal to the weight of the object. But here normal force is equal to mg. And centripetal force is equal to frictional force, which is equal to coefficient of friction times normal force, that is equal to mg. But from dynamics of circular motion, centripetal force is equal to mass times centripetal acceleration. This is equal to mv squared divided by r. M goes with m, mu times g, coefficient of static friction, times g is equal to v squared divided by r. And this is equal to v is the square root of coefficient of static friction times g times r. This is the velocity of a car turning around a flat curved road. But if the speed is greater than this value, the sideway frictional force cannot prevent the car from skidding sideways. Therefore, roads must be banked. We will see the motion of cars around a banked road. Before that, let's do example. What is the maximum speed at which a car can round a curve of 25-meter radius on a level road if the coefficient of static friction between the tires and the road is 0.4? Solution: given that coefficient of static friction is 0.4, the radius is 25 meter, and we want to find the maximum speed, V max. Since V is equal to the square root of coefficient of static friction times G times R, V max, this is the maximum speed that a car can round around a flat curved road of radius 25 meter with coefficient of static friction 0.4. Therefore, 0.4 times G is 10 times R is 25. This is equal to 10 meter per second. This is the maximum speed. If the speed exceeds this value, the sideway friction force cannot prevent the car from skidding sideways. In that case, roads should be banked. Therefore, let's consider a car turning at the corner of a banked curved road. This is the banking angle theta. And here, the normal force has two components. This normal force has two components. One is vertical component and the other is horizontal component. This is vertical component and vertical, and here this is horizontal component and horizontal. The vertical component is n times cosine of theta. The horizontal component is nh, n horizontal is equal to n times sine theta. And the vertical component is nv is equal to simply n times cos theta. For the centripetal force to exist, this centripetal force is equal to simply the component of the normal force along the radial direction. This centripetal force is equal to n times sine theta. The horizontal component of the normal force acts as a centripetal force, and this is equal to m times v squared divided by r. Along the vertical direction, we have NV, N cos theta balances gravitational force mg. Taking the ratio of both sides, N goes with N, sin theta over cos theta is tan theta. This is equal to M goes with M. This is V squared divided by GR. Theta is the banking angle. R is the radius of curvature of the rod. This is the speed with which a car can round around a banked rod of banking angle theta without depending on friction. But there are conditions by which the centripetal force depends on frictional force too. But here in this case, the centripetal force only depends on the component of the normal force. Having seen this, let's do an example. A curve of radius 30 meters is to be banked so that a car may make the turn at a speed of 50 meters per second without depending on friction. What must be the banking angle? Here, given that the radius is 30 meters, V is equal to 15 meters per second. What is the banking angle theta? From the relationship between banking angle and the speed, tan theta is equal to V squared divided by GR. This is equal to tan theta is equal to V squared, 15 meters per second square divided by G is 10 times R is 30 meter. G is actually meter per second square. Here meter square per second square. Meter per second square times meter is meter square per second square. The unit will go and we are left with tan theta is equal to 15 square. 15 times 15 simply divided by 10 times 30 by 15, 1 by 15, 2 by 5, 3 by 5, 2, 3 over 4. Tan theta is equal to 3 over 4 means theta is equal to tan inverse of 3 over 4 is equal to 37 degree. Therefore, the banking angle is 37 degree. And this is all about today.